for hydrocarbon maturation. Right? So, and to do justice to this subject, I have the honor and distinctive privilege to introduce to you the speaker of today's YP Monday technical meeting. He's a renowned geophysicist and environmental scientist with the Shell Petroleum Development Company. He has been with Shell since 2015, and having also worked in different places before then, he has carried out a lot of projects for Shell, both in the onshore and the offshore areas of Niger Delta Basin. He was also a member of several technological advances that have taken place in Shell, including full waveform inversion technology for seismic velocity model building. His areas of specialization include geophysics, especially in the area of data acquisition, processing, and quantitative interpretation. He's also an expert in environmental studies and radiation through earth physics. He's also interested in digitalization, which is with great interest in Python and machine learning and how they apply to geophysics. He's currently a visiting lecturer at the Center of Excellence in Geosciences and Petroleum Engineering at University of Benin. And when it comes to education, he's very learned. He's very vast in education. He has a BSc in physics from Delta State University, Abraka, an MSc in petroleum geophysics from the great Imperial College, London. He also has another MSc and a PhD in environmental studies and radiation through health physics from the prestigious, unique University of Port Harcourt. As we have seen, the speaker is an authority in this subject, having seen his educational qualifications and his work experiences, right? And he's well equipped and ready to bless us today with a lot of knowledge. In addition to all of this, he's also a family man. He's blessed with 2 kids. And he also indulges a lot of extracurricular activities like watching and playing football, traveling, and playing chess too. So ladies and gentlemen, join me to welcome Dr. Jude Osimobi, who will, by the end of today's presentation, make us understand the applications of basic physics in exploring hydrocarbon. Before I finally hand over to Dr. Jude, I would like to say that the presentation is meant to take 35 minutes. Questions and answers will follow afterwards for 15 minutes. And I will implore everyone to ask your questions at the end of the presentation. But if you feel you might forget your questions, kindly use the chat box, right? And when it's time to ask questions, just use the raise hand option, right? So I will finally, at this point, I will allow Dr. Jude the floor to make his presentation. Welcome, Dr. Jude.
Thank you very much, Robinson. Thank you. And thank you, SPE. Thank you, the co-chair. Thank you for the branch chair. Thank you for everybody on this call. I already see over 45 persons dialed in. That's quite interesting. And I want to assure you that God's willing, hopefully, by the time this section ends, we would have had a very wonderful run. Without wasting much time, I'm just going to share my screen. And let's get started so I could make the best use of the time. Okay, could you please confirm you can hear me clearly, see me, and also see the screen?
Yes, I can see your screen.
Okay, thank you very much. So this is the subject of the day. This topic has been mentioned, time without numbers. So I don't want to talk too much about it, but I just want to tell us that I want to have a lot of illustration. So there's going to be a lot of throwback for some people, reminder for some people, new knowledge for a lot more. So the idea is that because I've looked at the audience, it's quite vast, cutting across different areas of specialty. So I'll try to start a little and we'll gradually ramp it up just a notch, I promise. But to make it easy for us, just think about this. This guy there, consider him as the messenger, consider him to be myself. So you're sending me on an error and it's going to come back with information. What we do with those information, first of all, what is that? What's the wavelet and how we acquire it and how we use it to understand the subsurface? As I put in the intro, the earth had already blessed us. Nature has already blessed us, but we just need to do a bit more, which is use science to understand what is in there. And then if we do that, enormous resources await us. Just for expectation, I just want everybody on this call, sorry, this is maxing my screen. I just want everybody on this call to have a clear understanding of some of these basic physics principles and maths. And we'll focus a bit more on how we use those principles to solve seismic data processing issues, a bit on pre-processing, velocity, and imaging. We'll talk a bit more about that. And then general applications of that to maturing hydrocarbon. So the focus today will be to remind us of those basic physics key principles and dust it and tell us how we use this to mature hydrocarbon. I'll try and go a bit faster. So these are the things we hope to achieve today in terms of agenda. We'll talk more a bit more on signal theory. The engineers will be glad to see this. We'll play with some of the maths quickly. And we go into the bit of seismic processing where we use these theories, these signal approaches to solve problems like refraction statics, tomography issues, tomoplus issues, topographical issues, noise issues, deabsorption issues, deconvolutions issues, touch upon velocity, which is the medium for migration to happen effectively. So first, signal theory, just some basic physics. I want to start this by reminding us this experiment we normally did in high school, at one point or the other. And then we put in 2 pins here, and then we'll put a mirror here. And the experiment is mostly to try and track this back. And then we'll measure the incident angles and the reflected angles. Basic physics. I'm sure we all remember this. This is the same physics principle that we use to image the subsurface, whereby we send in sound, and then it hits our earth at different strata and come back to us. And you agree with me that the received information of this wavelet carries information of this environment. I'm going to go into pointer. So basic physics. We're not going to do anything more than this, but this, as basic as it is the foundation for hydrocarbon that we have today. Another one I also want to remind us is, we remember this glass prism experiment, whereby we also put in pins here, and then the light goes into the prism, begins to bend, begins to get transmitted. Of course, some will reflect back, some will refract because it's moving from different medium. And finally, we track it here. Simple physics again. So these are all principles we're going to be looking into, and that will help us understand this. But let's look at another, putting them in one slide, the laws of reflections, right? We have the incident rays, and it hits a reflection. On the normal, it comes back as reflected rays. These reflected rays carries information of this surface. The same thing when we clap our hands, principle of echo, the sound bounces back to us when it hits this. So this returned signal is key for us. A quick reminder again, when some of this ray goes through different medium, depending on the density, depending on the velocity of the medium, the ray is bound to change, either bend away from normal or move towards normal. And we also remember the critical angles and the principle of total eternal reflection. Please keep all of this in mind. We'll unravel them, but these are the basics. And this is where it all starts, high school physics. I promise I'm going to keep this simple. So we'll quickly remind ourselves, what is even a wavelet? It's a curve similar to that of the sine function, having a phase, period, amplitude. Now remember this again, the amplitude, remember the peak, the zero crossing, the time, all of that. And we describe it with this simple sine function. We remember the phase and all of this. So these things are very important because it's on these basics that the rest things we will see in maturing the hydrocarbon will build its roots. So this is the foundation we are already laying. A quick reminder again, what amplitudes are, I'll go quickly, what periods are, what phase are, what frequencies and wavelets, very important. And for my engineers and a bit of advanced physics, you begin to see when you move, you do some Fourier transform, you move from time domain, you go into frequency domain. And when you move from time to frequency domain, you've got, it splits into an amplitude spectrum and a phase spectrum, basic physics and maths. And you can always go back. And that's exactly what we do. Because there are some operations that we need to perform in time, because you can discriminate the signals in time. And there are some you take to the frequency domain because you could better discriminate it in the frequency domain, basic physics. And the reason why we want zero phase, minimum phase, all of that, it helps interpretation at acquisition. We want the minimum phase to let our energy get deeper and conserved. But processing, we want it at zero phase because then that's where the energy stays at the peak. It's causal. Interpretation wants that. Brilliant. Minimum phase, zero phase, all of that still applies. And then this is what a typical zero phase would look like. You see the peak amplitude at zero, and the minimum phase, have some of the amplitude on this way and some on the other way. And then when you also bring them into frequency domain, you have your amplitude and you also have your phase. Simple. One other very key thing we want to pay attention to is the fact that when we acquire seismic data, the volume of data when it's in an analog form is huge, right? So we don't need all of that. We oftentimes would discretize it. We pick certain areas of the signal that can tell us the story eventually. We'll resample them. In acquisition, we can sample it at 2 milliseconds. We resample at 4 milliseconds. But whilst you do all of this, you keep in mind of aliasing. It's also a very basic concept. There's a way you oversample the signal, you distort the image itself. So Nyquist frequency helps us pay attention to this concept to ensure that you don't go beyond that, because there are also at frequencies where your noise begins to wrap around that, you begin to struggle. In that case, it means that it's sharing the same physical properties as your signal. Typical illustration, we'll have a continuous analog signal, moving everywhere. But when you resample it, you vary it and take it at different interval. You sort of discretize it because that's what you want. You don't want that continuous signal for two major reasons: for storage, and also it still gives you the same information you need. But you have to be careful of oversampling. The same basic, so we are getting into the wavelet itself proper. So when you have a signal of this nature, you could find yourself, you densely sample it, which might not be what you want, or you poorly sample it. So if you poorly sample it, how would you use this red signal to describe all of this? So you're bound to have aliasing, you're bound to have a wraparound, you're bound to have issues with the image in question because you haven't properly sampled. So finding the right balance, the Nyquist frequency guides you so that you keep the right information you want in the data set. Another very basic principle, again, convolution, very key, because eventually this wavelet that we'll talk about, the Mr. Wiggle, gets to convolve. You convolve with filters. It gets to convolve with Earth, which is its own natural filter. So just a reminder of what convolution is about, and you have an output. So when you convolve an input with a filter, it gets you an output. In convolution is similar to cross correlation, but you don't flip. We'll get to that. In frequency domain, convolution is done by multiplying your amplitude and then you add your phase. An illustration. So think of this as a filter. You've got your input, You want to do something to this input, and that's why you've designed a filter. You probably want to cut out the high ends. You want to take out noise that exists at different frequency, that has different characteristics or physical properties. You want to do something to it. You also want to add it to this input signal, and then you have some sort of an output. And that's typically what the filter will do for you. Let's assume a case where we have a spike, you get it through a filter, it convolves with the filter, and then you have an output. You know, the same thing with an impulse filter this time around, you have an output. So whenever you hear the word filter, think of it that what would definitely distort positively or negatively your input wavelet. And this input wavelet will refer into, go back from inception, think of the mirror experiment. It's going to come back to you when it hits the surface. And that signal is where you're interested. You want to clean it up, you want to reorganize it, you want to deconvolve it, you want to get it the best principle you can to get a good subsurface image. That all of this is just to remind us things around filters. And when you come into the phase domain, all of this is for the time. When you come into the phase, again, remember that in phase, you multiply your amplitudes. And in in frequency domain, that means you multiply your amplitude and then you add your phase. So that will give you your amplitude spectrum and then your phase in the frequency domain. Summarizing all of that that we have to do between the time and the frequency domain. In time domain, when you have an input waveform, you convolve it with an impulse response, you get an output. You use Fourier transform, as we know, basic maths will move between time and frequency. You know, you could go the either ways and come back. In frequency domain, you've got an input spectrum, you multiply your amplitudes, amplitude in frequency response, and then you get an output, then you add the phase spectrum. So let's begin to throw some of these things, you know, to make more sense to us. When you have an input seismic trace, and the seismic trace is a convolution of your input wavelets and your Earth reflectivity. But of course, it gets mumbled out with noise. It's fine. You're not worried about that because you can handle it. And the next big thing that begins to happen is that the reflection coefficient itself is a product of density and velocity. So whenever you hear that, you remember that you're dealing with your density of the medium, which is why the glass prism experiment will always bend because you're moving from different media, and that's what you find between density and velocity. And that's in itself, the reflectivity itself is a product of each of them in the different mediums. And you take that, and that gives you the reflection coefficient. We'll see all of this in a more practical sense, but this is just to, when we use those terms, just to make sure we sort of understand it. The first experiment. Remember this, and then we'll talk about, we'll have an acoustic impedance, which is Earth itself, right? When you differentiate that by normal math differentiation, you have reflectivity, so they're sort of both the same. And then when you convolve it with this, remember this is the input sound wave that will send. When you convolve it with this, it gives you a seismic trace. So whenever you see a seismic section, it's an accumulation of traces. We'll see that. But because if this wavelet makes this seismic less of a spike, so you're not able to differentiate thin beds in the hydrocarbon sense, you want to deconvolve it for some reason to take away reverberations, to take away, to make it spiky, to resolve your thin beds, you deconvolve it, and you go back to your reflectivity. So this is how seismic is generated, and this is what an inversion would look like. And then you go back to your acoustic impedance, where you will begin to relate with the Earth properties itself. Your density and your velocity gives you this. So a typical recorded seismogram can be a model as a result of the convolution of the Earth impulse response with that of your input seismic. Let's do an experiment. So think of an Earth subsurface, like you're drilling a borehole, you've seen where someone dug the ground. First of all, you could meet something that looked like sand. You go a bit deeper, you meet something muddy or shaly or clay. You go back again, you could see some sort of sand. You could come here, you meet some hard rock. So this is what the subsurface could look like, all the way into several kilometers down for the engineers. When this happens, the acoustic impedance, remember that experiment, where as it's moving, because the velocity and density of the next medium is changing, it will either go right or left because you've met something else. And that will keep happening as the whole of the graph will go back down. So think of it that you're plotting a graph. And then you have a source wavelet, and let's assume a spike for this experiment. Your reflectivity, which is the Earth itself, would also behave in a spiky way. When you convolve this source wavelet with your first reflectivity, right, you're going to have a seismic trace. And because you're convolving, remember, it's acting as a filter, you're doing the mathematics of convolution. And then when you do that for the second layer, it's gone past the first layer, it's moved in deeper, you're also going to get a seismic reflection. Note that you begin to see that there are varying amplitudes and also difference phases. And this is dependent on whatever emits. Let's not talk polarity here. Let's just take width, hard or soft. So this experiment is going to run through the entire strata as much as your seismic input energy can carry before attenuation, absorption, and the rest would affect your input seismic, and then it loses of energy and dies out. So as far as it can go, it will keep going there. And then the accumulation of all of this will give you a synthetic seismogram. When you pull all of that together sorry, can someone please mute? When you pull all of that together, you begin to form the seismic we have. So you see how all of that is fusing in? You begin to have red, blue, whatever color you choose, hard, soft, which is sand, non-sand, as the case may be. A quick reminder of correlation, because we also use this principle, is different from convolution, because in convolution, you flip before you multiply. But in this case, A convolve B is the same thing as B convolve A. But in correlation, A correlate B is not the same as B correlate A. Just keep that in mind. And there are very two basic types, the cross correlation and the autocorrelation. Cross correlation is very key because we use it that's when you correlate it with itself. We use it in quite a lot of things we do. I'll show you that. And also the length of the cross correlation function is the sum of the length of the two waveform. Cross correlation is key in what we do in seismic to well tie. If you've ever had seismic to well tie, which is essentially an operation where we tie our well data with the seismic. And also we use cross correlation in residual statics and for the time shift. Now let's get a bit practical. I'm sure we all sort of enjoyed all of those basic maths reflection on some of those concepts. So let's do an experiment. Now, someone, for some reason, several years ago, it's been studied that hydrocarbon or sands will be found here. I don't have enough of time. I would have gone into that. Once upon a time, deposition happened, sand gathered, come into a depression called a basin. Think of a basin of water, poured sand in it. You observe that over time, as sedimentation keep happening, as sea level keep rising and going down, compaction is going to happen. They're going to move down quite intensely, and the temperature is going to rise, and kerosene will start cooking in the kitchen. And kerosene is a unit cell of hydrocarbon. So over time, that has been studied by geology. But now what we are doing is, and after that has happened, physics takes over. These are principles of millions of years. The Niger Delta, or the deltas that we have it today in the UK and everywhere in the world, took several millions of years to become what it is. And the first step will be around where are the thick sands. You could do your magnetic, aeromagnetic, aerogravity, whatever geophysics tool that can help you use magnetic susceptibility, gravity differentiators to find where your sands and your non-sands. So we are assuming all that has been done, and you want to acquire a seismic. So you have, in the case of a land acquisition, you have a vibrosite. Remember that physics basic principle where you send in light or you send in sound. It's going to hit each of the surface and come back. And these are receivers planted here. These receivers are carrying the information that this wavelet is going to hit and return back. And this information is key, is what we are going to talk about a bit more. The same thing in an onshore setting where the terrain is a bit more rugged because of shallow anomalies, because of unconsolidated layers. We have to always use dynamite so we can bury our source wavelet. Otherwise, the energy will dissipate even before it goes deeper. And the same basic physics, it's all going to come in here and go back, meeting all the strata as long as the energy can carry it before it dies out by attenuation. Remember how we formed an experiment and we put all of those wavelets together and we begin to combine them, convolving them with the earth reflectivity. By the time you put all of that together, we call that stacking. An image like this begins to form. And you can see clearly the images we are looking for are structures that are anticlinal, structures that are fault bounded, structures that have possible three-phase, two-phase fluids of water, oil, and gas. And every other minerals, this principle still holds water. So typical seismic, you're targeting this area, you draw up your 3D, you create your beams, and you begin to shoot and you receive. So you have your midpoint, you have your source, you have your receiver, very, very important. And then you send in this wavelet as your source wavelet, and it's going to hit this reflection and come back. And at each time it hits this reflection, something is always going to happen to it. And that will tell it, have you met a sand or have you met a shale? Let's just leave it as simple as that. Have you met sand? If you meet sand, the density of sand is different. The velocity of sand is different. So the behavior of sand will be different from that wavelet. If you meet a non-sand or a shale, the density is different. The velocity is different. So it's going to be different when it says that. Typical seismic can be in 2D when you have very sparse line, or can be in 3D when the lines are becoming together, just survey plans. And then you have 4D when you had a 3D in the past, but you want to know what has happened over a period of time. It's called time lapse. So let's say you used to have this reservoir, you have gas, oil, whatever color connotation we work with. After you've produced it through this well, think of a well like when you soak a foam in water. What would happen when you put a straw into that foam? At that high pressure, capillarity is going to take place. Basic physics. You remember those test tube experiments you did? Once you put in a straw in a pipe soaked in water, by natural capillary pressure, the water will want to go through the conduit of the pipe. And that's what we do when we drill a well. The reservoir of sands have pore space like a foam or a sponge. And because it could hold in hydrocarbon, you drill in your well, the hydrocarbon. Hello? Hello?
Let's go ahead, Captain J.
Oh, sorry. So all of that is going to happen and you're going to produce this field. But after a while, things are going to happen and production would affect the field. So 4D means reapply it and text the difference between seismic B to seismic A. We call this the monitor, and we call this the monitor 1, and you call the original seismic the base, right? So you check how has it fared between before and now. You would always see difference when you subtract the two seismic, when all acquisition principles stays at least reasonably the same, where the repeatability is as high as it can be. Okay, now we've talked a lot about all of this. Let's get into action. An acquisition geophysicist, as it's called, would naturally design this survey, ensure that the subsurface he wants to capture is covered. And then a processing geophysicist, think of it as a photographer, all of these people as a photographer. When a photographer takes in a picture, it takes a picture and it stores in a flash. Olden days photography, I meant. I don't know how many people witnessed it. I did. You take it to the lab, and then the lab washes it. It cleans it out, takes away the noise, takes away what you don't want. And then what looks like an image begins to come out. But that picture will not make any sense until an interpreter looks at it and says, wahoo, this is a picture of Jude. So the interpretation, and that's all that's happened. A photographer takes a picture, he takes it to the lab for processing, and an acquisition says what it is, interpretation. But we are going to focus a bit more in the processing, because that's where the granularity happens. If you distort the wavelet at that point, the interpreter don't have anything to make of that image. So it's quite very key to pay attention. And this is typically what it will look like. If you remember that, when we stack all of this energy together, this is not as noisy as it will be. This is just for illustration. You will rarely make sense of this image because it's all marked with noise. It's all marked with your wavelet has been distorted. A lot has happened. But a typical seismic processing step will take you from what looks like this in the left to what looks like this in the right. I'm sure if you're an interpreter, you would appreciate this because you can see your faults. By fault, we mean that the hydrocarbon can be held down until a well is drilled in here. And you can begin to see those anticlinal structures. So these are potential places, excuse me, for interpretation. Will we now say that processors are magicians? How have we moved from left to right? And this is a question we'll answer in this presentation. So typically it will look like this. You have a refraction statics, you denoise it, but you must have the basic signal processing understanding. Otherwise, you won't make sense of this. But in every project, no matter how we design the survey, we are always constrained. We are always constrained with quality, time, and cost. So we can never get all of the time to do everything. We can never get 100% of quality. Cost will always be a constraint. So typical project management, just like whatever anybody does, we're always constrained with these parameters. Let's take the first, refraction statics. We already know that because of different, I'll illustrate with this picture. So imagine when you're walking a place that is hilly and comes down, it goes up, it comes down, it goes up, it comes down. When you shoot your array, this will pick it at different points, even if they are supposed to be flat. And some of the assumptions we make is that the earth is flat, but that's not correct. But because this had happened, the hyperbola, which is the mass of your NMO, will not work well and it will not be clean. So you won't be able to solve this maths because you don't have a clean hyperbola. But when you correct for refraction statics, you bring everything down to a flat datum. You assume a flat datum, correct for the velocity of the underlying of the weathered layers, and you have a cleaner hyperbola in such a way that when you collapse it and stack this image, different signals, you're going to have a constructive interference. Just a bit of illustration. When you have this, you put a seismic, you put your ground elevation or shot location. You have your different parameters. You already designed this, so you know this. To correct for refraction static, basic maths again. But the major thing we look out for is replacement velocity. The replacement velocity can be got from several means. You can design an oppo survey. You can run a refraction seismology. You can get it from your first break smartly because you also know that your reflection seismology also carry your first break, or you can assume it from prior knowledge. What we normally do in the industry is to use the first break to do an inversion, tomographic inversion to get back our replacement velocity. So once you do that and apply it on the data, I'll just toggle a few times. We can see this image here is so distorted because the interference here is destructive. There are no hyperbolas, are not clean. So the NMO equation could not be solved. You could struggle to make much of this image compared to when you have solved for this. You see how events are lining up properly, like a typical seismic should look like. And that's what we achieve by the operation refraction statics correction. Then let's talk about noise. You saw that whenever you get a seismic signal back, you don't get your impulse wavelet again. Noise also comes along with it. Types of noise varying from spikes, ground roll, noise train, line noise, swell noise. At any time a seismic acquisition is going on, we all are agents of noise because a mere stamp of your foot on the ground will be recorded as a spike. A mere drop of a mango from the tree will be recorded as a noise. And noise for us is an unwanted signal. Anything that you don't need, depending on which operation you're carrying. If it's a reflection seismology, your reflectors are your signals. Every other thing are noise. If it's a refraction exercise, your energy is focused on that. If it's a full waveform inversion, your direct arrivals and your first breaks become precious to you. So once you liken the noise of noise attenuation to be like this, you have this dirty water. I don't know if any of us ever used a filter to filter their water. You pour all of this here and you design a filter so that clean waters can go past. This filter is all mathematical algorithms and it doesn't cost anything. You are only merely relying on understanding the physical properties of frequency, amplitude, velocity, and all what physical properties you can lay your hands on, and use that to design your discriminators. And that's where you perform some sort of data science. They are all science of the data. If you understand them and you discriminate them, and then you have clean waters. One of the noise that would always have in Delta in most land operation is you have your seismic. Behind it are your signals. But you could see that there is this what you don't want, maxing this data. These are rarely waves, if you go into the types of waves. You see, but because you understand their characteristics, ground rules, for example, are high amplitude, low velocity, and low frequency. Because you understand how they exist, because you know that these properties of them exist. The velocity is around 600. You don't expect your signal to exist at that velocity, at that depth. So because you understand those physical properties, all you then do is to design a filter. Remember the concept of filter, where you take all of these data sets through the filter and what you've designed your filter to be, which are not, you don't want your dirty waters to go past. And you can see what it looks like after you've designed and attenuated for ground rule, and see the difference. And you can see clearly how the noise is sitting nicely. So you're just doing data science and using the properties of the data to answer your question. The same thing with a spike. When I mentioned that when any of us are in a seismic environment and stamp their foot on the ground, once you stamp your foot on the ground, it's going to be recorded like this. The geophones or hydrophones are sensitive enough to pick those signals. And once it's picked, but you can see clearly that this stands out with the neighboring traces. Again, looking for data science discriminators for these things. Because they stand out differently, you're able to design a filter to be able to take this out. And this is what you get after you successfully do that. And while you are doing all of this is to be able to have an image of the subsurface. And you could clearly see what a pre-processed before pre-processing seismic would look like. I'm sure nobody here can make any image out of this. Nobody sees anything because it's all marked with noise, ground rolls, spikes, noise trains, and what's more. But after you take it through the processing and design several filters, this is just me talking about this. This could take months of tedious work, and design several filters. You begin to have what looks like a good image of the subsurface. So when you see this, just picture a slice of the subsurface inside, and you're inside it, watching it and seeing what Earth has given to us, what God has blessed us with. So this is just like a slice of it, and you're sitting inside the ground. This is what you are seeing: sand and non-sand, all through with colors. The same thing also, another area we will struggle is that the amplitude will not always balance. And because of things around coupling, things around terrain, sometimes the energy is low. But this is also very important because we know it's not real. We know that's not how the subsurface, the ground is underneath. There's nowhere that will look like this. They could, but in this case, this is an anomaly. So you try to compensate for this by designing a process to make sure you fill these energies in. And you can clearly see once you've done this, you fill it up with the right amplitude. Lastly, on the pre-processing, we talk now when you convolve your wavelet with the earth, it makes it less spiky. It makes your energy, it makes your team bed not being able to resolve. Then what you need to do is to deconvolve it. If you remember that mathematics, you deconvolve it so you could go back to your reflectivity and perhaps eventually get to your impedance itself. So when you do that, you see that the spikiness of things like this will become tighter in the end. And if there are team beds, by team beds, I mean places in the subsurface. So you see how dark this is. Think of you have drilled, you have torn a land itself, and you are inside, sitting there inside the borehole. These are all what you're gonna see. But you don't need to go there because you're going several kilometers. But geophysics principle has been able to take that photo for you and bring it up for you to make your analysis. Now, let's talk the final part of things, which is migration. We can see people are moving from different places. where they belong, where they find peace, where they find happiness. Immigration always would happen. People will always move around to meet their loved ones, to find greener pastures, for studies, for whatsoever. But the migration we're talking about here is not to put human beings to where they want to be. But this time around, we want to move seismic signals to where they belong. Because unless they are positioned where they belong, up deep, you will never make good meaning of their images. One very important concept before you can migrate is the medium which you will migrate, and that's velocity. When you talk of time, think of remember your velocity, distance over time. Offset this time around and time. The slope between both of them is our velocity. I wouldn't sweat too much about this. I will just tell you, when you see a gather perfectly flat, you know that the velocity is correct. When this gather is not all flat, and then it's still coming late, you say that the velocity at that point is too slow. So that means you need to give it a faster value to be able to be flat. And the same thing when it curves upwards, it becomes too fast. I think that is enough for now. And let's see what it looks like in a typical stack lamp or gathers, right? You can see this curving upwards. If I had time, I would have taken this as a quiz. Would we say that this velocity is too fast, or is it too slow, or is it normal? Your guess is as good as mine. We perform travel time tomography by picking this in the form of RMO and use those peaks to run a travel time inversion, just the same way our medical tomography happens, where you try to use your observed and your modeled, and you find the velocity that should give rise to such image. And that's what we do in medicine. It's still the same concept of imaging that we use in this case. So when you correct for this velocity, you will clearly see that things are beginning to get flatter. At least this velocity begins to get more accurate than the one we had before. That's it for velocity analysis. And once you have done this, you would always have a simple initial model to start with. Again, this is the velocity of the ground you are in now, because velocity is key. It also has density. You also have other properties, but we are focusing on velocity because that's what will determine the distance and time relationship. So think of it now that you are still in a well, or you have a ground that is dug up, and this is the kind of velocity you will see. So naturally, the velocity will be slower at the shallow because they are not compacted, they are not faster, they are not hardened yet. As hardening or compaction takes place, the velocity would naturally begin to look faster. But because there are also geologic reasons why velocity can have some sort of reasons, you now have to look at it with respect to geology. One very key thing, I'll rush this quickly, is the full waveform inversion, right? Full waveform inversion helps us to build high resolution velocity, by checking the difference between your synthetics and your field data. So you have a starting model, you do a forward model to get your synthetic seismogram, you check the difference between your field observed data and your synthetic seismogram, and you find your residual. And this goes back into your model updating. And until you have the least misfit between the observed and the modeled, that is when you can say that the model is relatively correct. Now you have a correct velocity. You now want to image. You now want to migrate. Like in migration, like when you take a photo with your phone and the image is blurred, it doesn't make sense. And the reason is because the wavelet, the pictures, the pixels are not sitting where they should sit. They are here, but they have not been positioned where they can make constructive sense. So migration moves them, of course, with some maths and physics principle, moves them to the right position. And after migration, you have improved focusing, spatial and vertical resolution will be enhanced. Event continuity will be improved. And then you can begin to see what this beautiful lady looks like because you've improved focusing. And that principle is called migration. Let's see. When you migrate, your steeping dips, your anticlines become smaller, your synclines. By anticlines, I just mean, think of a hill inside the subsurface, become smaller, and your synclines become wider, your bow ties become loosened. These are just as a result of errors. They are not well positioned, so you put them there. When you do that, you can see what has happened in this part of the image. This was before an old migration, you could see how it looked like. But when you do the right migration and put things where they should be, just like the image of that young lady we saw, things became a better result. There are varying types. One, in terms of the time migration, one assumes that the ray does not bend just because they want to keep the maths simple. And this worked in the times of our fathers, where the math was simple for some other reasons. So you want to assume the mirror experiment, you have your incident, you go in, you come back, you go in, you come back. Very simple, and you take this simply. But the depth migration begins to get a bit more complicated. It begins to honor the principle of ray bend. So whenever you think of time and depth migration, just know that one honors ray bending, one assumes that the ray, the wave is a straight line, but this honors it. There's a more complicated one, which is similar to the full wave.
Doc, time.
How many more minutes?
Time.
Yes.
Right, the time is
okay,
almost
to round up.
To
round up, I'll just talk a bit more about the kickoff migration. Just think of a kickoff migration. Most of the things we do in geophysics, apart from the filters, apart from the convolving, apart from all of the other things, we do a lot that has to do with modeling and trying to get your actual to look to your model. So when you solve a kickoff migration, this is the algorithm that makes your model and your actual to come to an agreement. Take, for instance, for a point scatterer, you need to design a diffractor curve. I'm using the simplest of words and trying to keep it as simple as I can. But just all what you're trying to do is you want to move things in the right position where they belong. And for a typical project, you want to be able to solve this. You have an initial model, you take it through a pre-stack, initial model and an input data. You take it through the engine of migration. You get a residual because it's not fully correct. You cannot most times get it correct once. You do that again, you do a travel time inversion of the peaks. And if it's not correct, if you migrate it and check if it's correct. If it's not correct, you could go through this loop for a number of times until time, quality, to as much as you want before you go to your final image. And that's exactly what has happened to this data. It's gone through pre-processed. It's taken out all of the noise. It's compensated for the refraction. It's been compensated of the deconvolution and the wavelet effect. A lot amplitude has been balanced. It has been migrated to the right position. And that's where you see that this before and after. So I ask again, are processors magicians? They are not. They simply use basic physics, study the wavelet, discriminate and reconstruct the desired signal based on amplitude, frequency, phase, velocity, and every other physical properties that can discriminate them. I check again. Did I meet your key expectation? Do we clearly understand the applicable physics principles of reflection, of refraction, of ray bending, of deconvolution, of convolution, and all of that? Did we also go through the pre-processing? Have we corrected? Have you seen how refraction statics can be done? Have we seen how noise can be attenuated by designing filter? Do we understand velocity better now? That when it is flat, velocity is correct. When it's slow, velocity is coming down. And when it's fast, velocity is going up. Have we also understand the concept of imaging, time and depth migration? Do we see the Kerckhoff and the RTM equation, how that is the basics of everything we do, and how essentially all of this applies to hydrocarbon maturation? Thank you very much, ladies and gentlemen, for your time. Thank you for giving me a listening ear, and let's have a chat. It's Q&A time. Thank you very much.
Oh, thank you very much, Dr. Jude. This is really wonderful and mind-blowing. You actually took time to, take us back to fundamentals, right? So this actually shows that no knowledge is a waste. All our secondary school knowledge in physics, we see them in use actually here, right? So just a quick summary of what Dr. Jude has told us. So he has taken us through on how we can apply basic physics and math principles, right? To actually understand the subsurface, right? So we saw the principles we were used to in secondary school, like the glass prism experiment, the laws of reflection, and all of that. So we also took us through how we can use Fourier transform and other filters in seismic processing. So in all, he concentrated more on the seismic processing aspect, right? So he literally, and thoroughly took us through the basic workflow or the industry standard workflow for seismic processing. So we looked at refraction statistics, how you can attenuate noise to improve your resolution, deconvolution, all right, to improve your resolution. How you can do your velocity analysis, to flatten your event, right? And how we can also use full wave inversion to actually obtain the optimal velocity for your velocity analysis, right? So you also told us about migration, right? And how migration can help you refocus your subsurface images and actually bring objects to their right subsurface positions, right? So in the end, we see that what we've learned or what we are used to in secondary school are very much applied. And I want to talk to specifically to maybe some of our young graduates who are here. So no knowledge is a waste. Don't say I've forgotten. This is it's just a secondary school knowledge. So they are all being used. So you can actually go back to your textbooks and try to refresh yourself and get used to those principles again. They are very much applied in the industry, right? So I want to say thank you very much, Dr. Jude. It's been wonderful. Now I can say that I can actually I understood a lot of stuff, right? The principles and how I can actually use all of this better imaging of the subsurface and to have a better geology, right? Thank you very much. So the floor is now open for questions and answer. If you have questions, we'll have 15 minutes or 10 minutes for this, right?
So we have some questions on the chat. Robinson, you can please check that.
So okay, I'm going to look at it now. So I'm looking at it. So, all right. So, okay, so this one is coming from eBay, right? He said, good evening, Mr. Presenter. Sir, can full wave inversion techniques take care of effect of multiples and fault shadow on velocity model? Thank you. Dr. Jude, did you hear me?
Yes, I hear you clearly. There are some questions on the chat, but I was thinking there's a way you want to moderate it.
Okay, so I just read this from the chat, from eBay.
Oh, say it again. I didn't hear you.
He said, can full wave inversion technique take care of effect of multiples and fault shadow on velocity model? Can it take care of multiples and fault shadow?
So it depends. Of course, when you have your right velocity first, then things can cascade. So velocity gets corrected from top to bottom. So if you have a relative short fault shadow issue, which is a complex issue in the Niger Delta, I agree, you need your velocity to be accurate from the shallow. So your full waveform inversion, when you do your depth of penetration analysis, will tell you as far as in depth you can get your solution, because it's not typical what will go all the way down. No, it will stop at the first 1 or 2 seconds at max, right? So it doesn't get all the way to the deep. And that's why you need to know that. But once you resolve your shallow, that means your velocity is correct at the shallow. And then at least that gives you room to get an accurate velocity. Multiples attenuation would have been on this pack. It's a different technique, right? You need to study the physics again. Let's say if you have a multiple of your seabed, you need to look at how periodic it is. Is it coming at a particular time? And then all you need is just to say, if you do a predictive deconvolution, for example, you are able to take care of that. So again, you are still looking at what properties does this multiple have? And once you find them, which, for example, the water bottom multiple is a periodic nature, You use its periodic nature to attack it by itself. And then when you do an autocorrelation of itself, you clearly see where the multiples are. Thanks. I hope that helps.
All right. Okay. Yeah. Okay. Thank you. So this one says, this one is coming from Sharon Emerangini. He said, please, what informs the initial velocity model that we use before migration?
Very good question. Thanks a lot. The questions are quite brilliant. So what informs the velocity, the initial velocity? Two ways you can get it. First of all, you can assume any velocity. So what I mean by assume is with some sort of knowledge. You know principles that velocity, just like everything, will get faster as you move from top to bottom. So you can actually build your own initial model by saying, oh, water velocity, I've measured it is 1500. Loose sediment velocity, the next strata, I want it to be 1800, 1800. And you can cascade it then. The tool is able to, first of all, give you a wrong velocity or a semi-accurate velocity. It's now left for you to go back and find. Sorry, let me just end this call. It's now left for you to go back in time and find the right velocity. So you can start with everything. But the industry has advanced, and these days, there will always be an existing prior velocity, which is near correct. So you can use that as your own starting velocity, and then you update it to get the right solution. Yeah.
Okay. Okay. All right. Thank you very much, Dr. Jude.
Okay.
So, okay, let me check.
I mean, anybody that also want to speak can
yeah, if you want
unmute
to
or raise their hand.
you can just
good
unmute
evening.
yourself and ask your question, right? Raise your hand and unmute yourself, right? Okay.
Yes, Jerry, go ahead. I can hear you.
Okay, so you thank you very much for the wonderful presentation and everything that you've outlined. So for me, I'm looking at this from an interpreter's point of view, because sometimes I'm working with a particular data set, but some information that will be very key to my interpretation, they are not there, like they are kind of missing. Like for instance, I don't have amplitudes that will actually help me to know, maybe predict the extent of my hydrocarbon, or maybe the structure is not really optimum enough. So I really want to know, from your perspective, what could go wrong with processing that might affect the final image of the subsurface?
Thanks a lot, Jerry. Very informed question. So first of all, nothing would go wrong if everything is done right, because everything we do is wrong, but how right we are, as what's his name, this guy will put it, is what matters, because the velocity, we can't get it 100%, but how right we are away from wrong makes us right? So for a case of amplitude issue or anomaly, first of all, the first question is, was it acquired? Because if the data wasn't acquired in the first place because of some reason, maybe some platform existed there, it couldn't be acquired, something happened, there's no data there. If it's not there, first of all, it's not there. So you can't process what is not existing. But let's assume a case where it's there. Yes, a lot can go wrong. If I don't process in a broadband sense, I could lose my low frequencies, and you might not see this imaging that need low frequencies to be properly imaged. I could also lose my high frequencies, and then you are not able to resolve your team beds. I could do a wrong deconvolution, but of course the industry has matured, and that's why the craft of geophysics becomes a skill, right? But no processing, I repeat, no processing should happen in isolation with just the processor. At every milestone, at every processing achievable, the interpreter, they do it together. So this is a teamwork, whereby the interpreter will be invited periodically to say, what we are doing, how does it answer your question? And if it doesn't, because we process for reason, you cannot have a shallow problem and you are trying to get all your deep solutions. No. But you could have processed for that purpose, and 3 years down the line, the interest has moved deeper. So you reprocess, because the original processing was not targeting to solve that. You can't solve everything. The heterogeneity of the earth is vast. So you just have to pick your problem and focus on it and solve it. So it depends on one thing or the other. Amplitude, you saw when we talked about amplitude balancing, could go wrong. So, but when it's done, you check things like what I have shown you. Was it accurate? Was it good? Did you fill it up properly? These are some of the things that you do in QC. And a detailed technical processing shop will not miss that out, hopefully. Thanks.
Yeah, thank you very much. Yeah.
You're welcome, Jerry.
Robinson, are you there?
It looks like we lost Robinson.
Yeah, okay, so there's one more question on the chat.
Okay, sorry, I was muted, right, okay. Sorry, can you hear me now?
Okay.
Yeah,
Yes,
thank you very much.
she was saying there's a question on the chat.
Right,
yes,
yes.
please.
Yeah.
So from the chat box, we have another question that says, from Newton Jonathan. So it says, the process of migration, we understand that we are trying to match these logs so we can get a clear picture of what we are looking for. So how can we get an accurate interpretation of these images? What can we factor in?
We're trying to match.
We are trying to match these logs. So I don't know if we...
Okay, maybe I'm just going to explain. So you've sort of combined two things. When you try to match the log with your seismic, what you do is you're trying to do a seismic to well tie, right? And then you go ahead to get your synthetic seismogram for the well and put your well in time so you can marry both of them and find your tie. So that's a separate operation. Migration itself is that the image as itself, the subsurface image, is distorted. They are positioned at different locations. They are not at peace. They are not where they should be. So you are now using mathematical formulas to put them where they belong. So that's the idea of migration. I don't know if that helped. So first, you are not matching migration to the logs yet. It's when you are done with your imaging, you are now asking yourself, this red, this blue, this red, this blue, I don't know where it is. But a well has been drilled, which is where the well engineer comes in, the engineers come in. They've drilled it, and as they were drilling, they were seeing sand and shale, and they were logging it with their tools. But that logging, a gamma ray log, a density log, and some sort of log that you would need will clearly tell you what they have seen in the truth nature of it. The seismic, you did not go underground, you didn't see it. You only used your imaging. So you now want to know, what does this color mean with an actual well? Oh, I tie both of them at this point. So once you can tie them at where they tie and have a good tie, then you can believe the rest that your well has not captured. So, and that process is the cross correlation that we described. And that's a seismic to well tie. Thank you very much.
All right, thank you. Thank you very much. Okay, so any more questions? I think we're... Okay. Okay, so that will bring us to the end of the question and answer.
Okay, thank you very much. I hope we've been able to, touch some light. I see quite a lot of names cutting across different fields I know. Some people I know personally from different walks of life. I hope we've been able to understand at least what Jude does at the least. And thank you very much, SPE and the organizers of this meeting, for having me. We look forward to conversation that can take us anywhere. This presentation also will be made available. And at any time you have any question, do me an email and I will respond, hopefully. Thank you very much.
All right, thank you very much, Mr. Jude. That was a wonderful one. And I'm sure everybody also followed well and properly understand everything you said. Right. Thank you.
Hi, Robinson. Sorry to cut you in. A lot of persons are leaving. We went from 65 peak to like 40 something. So let's go ahead and take a photograph now. Then you can continue with the rest of the program, please. Thank you.
All right. Okay.
So please, let's turn on our cameras, our videos for a group photograph. Thank you, everybody.
Robinson, you need to stop sharing so we can capture that.
All right. Okay.
Okay. Can you see me?
It's a big mess. Please, let's put a smile on. That was an amazing lecture. All of us should be feeling very excited right now.
They see me.
Are we good with the pictures?
Just one more.
Okay.
I'm done. Give me your best smile, you know.
We are not seeing your own best smile, though.
Oh my God, SZ, I don't understand. My camera is
Your
misbehaving
video
at
is
the
not
moment.
on.
I know. SZ, you don't have to call me out. So my camera just stopped, like my laptop camera is not coming on now. So apologies for that. But I've taken. Nice one, guys. Thank you very much.
All right, go ahead, Robinson. Continue. Thank you, everybody.
Robinson, are you still there? Okay.
All right, can you hear me?
Yes, I can.
Okay, so let me share my screen again. All right, sorry. The next on our agenda is membership drive by Obianuju Ishikeli.
All right, good evening, everyone. Please confirm you can hear me.
Yeah, we can hear you.
Yes, I can. Good evening, Uju.
Yes, we can hear you.
While you're authorizing me to share my slide, I just want to say a very big thank you to Dr. Jude Osimubi.
Uju, are you muted? We can't hear you.
Oh, sorry, I was muted. So can you hear me now?
Yes.
All right. So I was saying that it's such a clear presentation, and it's noteworthy to say that this is one of the nicest presentation I've been with. I've been in SPE, especially when it concerns the young professionals. So thank you very much, Dr. Jude. So basically, let me share my slide. Okay. Please confirm you can see it.
Yes.
All right, so basically my mission here is just to let you know about SPE and how to be a member, especially to get great presentations like this, technical presentations like this, to stay up to date with industry happenings. So it's important to register as an SPE member, and most especially as a young professional with SPE Port Harcourt section. My name is Obianuju Ishikeli, and I am the YP membership team lead for SPE section 103. So I'll be talking briefly about SPE. So basically, a lot of challenges abound in the oil and gas industry, as well as a lot of issues to tackle. So one of the reasons why SPE came on board is to bring young professionals and professional members together, or even student members together, to share knowledge, experience, skills, and also exchange ideas about the oil and gas industry or the energy industry. So SPE happens to be one of the largest individual member organizations, serving members, engineers, students, scientists, and what have you. A lot of programs are being held every year, or at least monthly, in SPE. We have international events like NICE. We also have online resources where you can get papers and read papers for your articles or for your technical papers. You can also publish your papers on our journals. We also have regional events and community events, networking opportunities, and there are a lot of awards and recognition, grants, and scholarship that is being awarded, especially in SPE section 103. So I don't know how else to encourage you all to register if you're not yet registered as a young professional. And SPE is not just for petroleum engineers or geologists. It cuts across board because the oil and gas industry is a multidisciplinary one. So we have mathematicians, we have finance personnel, we have business managers, we have lawyers. So we'll need all hands on deck when it comes to evolving and energy sustainability. And if you're looking to transit from being a student member to a young professional, it's easy. Just make sure that there'll be no breakage during your student years in terms of your renewal. And once it's the end of your time as a student, you get an automatic 1 year free renewal as a young professional. And if you also want to register, if you were not a student member before now and you want to register afresh as a young professional in SPE section 103, you can do that through the SPE.org website, or you can do that through SPE Port Harcourt session by filling the form that will be dropped at the link at the chat box, the link that's going to be dropped at the chat box. Or you can reach out to me personally and I'll give you directions on how to register fully as a young professional with SPE. And if you're a student and you're here and you're wondering how you can be part of this organization, I'll advise that you check around, or you can also ask people around you or the SPE team or in the student, your student chapters close to you, so you can get in contact with your student president and they'll put you through on how to be a registered student member. And SPE Cares organize different kind of giving back to the society programs like community services. So it's not just about the technical talks and the presentation. We also give back to the society. So that's one of the things you get to gain from SPE. And you ask me how you can grow as an SPE member, or how SPE can help you grow. First of all, you get a constant in your professional life. Secondly, you have local and international participation depending on how visible you decide to be or you want to be. It also gives you an opportunity to network with different industry professionals and also get mentoring at the same time. And there's diverse learning opportunities like this one you're in now. And also you have corporate support. You have a lot of people in the industry that are ready to help you, are ready to listen to you and mentor you. So you have that corporate support, and you also have the opportunity to be part and also to give back to the society and to the industry. So to find more about SPE and the industry, I advise you go to spe.org. Energy